Okay, so today we will study some more number theoretic results, so which will be useful in our future studies of asymmetric cryptography. Okay, so today we will discuss about two interesting and important algorithms. One is called Euclidean algorithm, which is used to compute the GCD, or the greatest common divisor, of two integers, and also which is useful to compute the multiplicative inverse. So we have defined what is a multiplicative inverse. So we will see how the Euclidean algorithm can be extended to compute the multiplicative inverse, and then we will discuss about another very interesting algorithm. It is called Chinese remainder theorem. The theme is to express whole in parts. Okay, so we will see what is that, and then also conclude with some important results on cyclic groups, and also discuss about a test of primitiveness of an element. So previous results, if you remember that what we did in the last time when we studied about number theory, we studied modular arithmetic. So we have more or less seen what is meant by modular arithmetic, and the idea was that so Zn star was used to denote the set of residues modulo n that are relatively prime to n. So I hope you remember this notation. So Zn star means that if n is any number given, so n is not necessarily a prime number. So Zn star means all those elements, okay, when I am reducing the element modulo n, so which those elements has to, the residues has to be relatively prime. So they have to be co-prime to n, right. So therefore they should not have any factor with n except 1. Okay, so therefore they are co-prime to n, and Zn star is used to denote that particular set. So we have seen that Zn star forms a multiplicative group under multiplication. Okay, that means that Zn star essentially what we saw, every element has an inverse, right, has a multiplicative inverse. So any element inside Zn star has a multiplicative inverse, and Zn star is also closed under multiplication. So if you take two elements which lies in Zn star and multiply them, and also take a modulo n, then the result is also inside Zn star. So that is a closure property, right. So today we will take up an algorithm which is called the Euclidean algorithm. So I think all of us know this algorithm in actually. Okay, so therefore this is actually the same algorithm which we have used in our school days to compute GCD of two numbers. Okay, so the thing is that we will just study that little bit more carefully. Okay, so let us see that suppose two numbers are provided to us, a and b, and we have suppose a greater than b. Okay, so what do you do? Typically what you do is like this, that is you take a and you store a in a variable called r0, and you take b and store that in a variable called r1. Okay, then what you do is that you start dividing r0 by r1, you obtain a quotient called q1, and here you get q1 r1, right. So therefore so the remainder which you get is called r1, I denote by r1, and r1 equal to r0 minus q1 r1, right. So this is the remainder. So you get r0 here, and you subtract q1 r1, and you obtain r2. Okay, so that is actually r2. So that is, so therefore if you see that this I can actually continue, right. So therefore what I do is that next I take r1 here and I divide r1 and I continue with this process. So therefore at any stage, that is at any mth stage, I have got this particular thing, like I have got rm minus 2, okay, and I divide that by say rm minus 1, and I get here q m minus 1, okay, and I get here q m minus 1 into rm minus 1, and this remainder is rm. Okay, so rm is rm minus 2 minus qm minus 1 rm minus 1. Okay, so this is the corresponding result at the mth stage of this algorithm, right. So therefore now we know that we continue this kind of division, and when we get the remainder value to be equal to 0, then we look at the previous divisor value and report that as the GCD of these two numbers, r0 and r1, right. So that is the fundamental working of the algorithm. So I think all of us know this algorithm, right. So why does this algorithm work? So therefore this is the pseudocode of the algorithm. You see that r0 has been stored, a has been stored in r0, B has been stored in R1 and you start with m equal to 1, you compute the quotient. So, the quotient is the floor of when you divide Rm minus 1 by Rm. Okay. So, that is the so this is the Rm minus 1 divided by Rm and you get Qm, okay, and then you get Rm plus 1. So, Rm plus 1 is Rm minus 1 minus Qm into Rm. So, same thing you, I mean, in the particular equation that we wrote, you can also write Rm plus 1 equal to Rm minus 1 minus Qm Rm, right. So, therefore, this particular step is written out here. So, Rm plus 1 equal to Rm minus 1 minus Qm into Rm, and m equal to, you increment m each number, I mean each times, and when you get the value of remainder equal to 0, you see m equal to m minus 1, that is the previous stage, and you report the corresponding Rm as a of the previous, I mean which is the previous divisor, as the corresponding GCD. Okay. So, now what is the reason why this is correct? I mean the correctness of this algorithm can be seen by this particular equation set. That is what I am interested in computing is GCD of A comma B, right. So, what is A? A is R naught and B is R1, right. So, R naught is actually equal to Q1 R1 plus R2, right, and R1 is R1. So, therefore, if I take a GCD of these two numbers, because R1 is here and R1 is also here, this reduces to GCD of R1 comma R2, right. So, therefore, if I continue in this fashion, I get GCD of R1 comma R2 equal to GCD of R2 comma R3 and similarly, and then finally, since Rm is dividing Rm minus 1, so therefore, the GCD is Rm, right. So, therefore, this actually terminates this, I mean this algorithm gives you also correctly the corresponding GCD of A and B, right. So, therefore, the Euclidean algorithm can be used to compute the GCD of two positive integers, and it is also can be used to check whether an integer modulo n has a multiplicative inverse. How can you do that? How can we check? So, what is the check? Whether a particular element, whether a particular integer modulo n has a multiplicative inverse. We have studied this property. What is the property? Yeah, GCD of A comma n is equal to 1. So, therefore, what I have to do is that I have to compute the GCD and the GCD has to be 1. If the GCD is 1, then the element has an integer, I mean has an inverse, multiplicative inverse. Okay. But the question is, how can I compute the inverse? That is the next question. So, therefore, I can check whether an element or whether an integer modulo n has a multiplicative inverse very easily, but the thing is that I am also interested to compute the corresponding inverse value. Okay. So, this particular algorithm is called the extended Euclidean algorithm. Okay. So, therefore, let us study or let us try to compute the inverse of 28 modulo 75. Okay. So, so therefore, if I am I mean what I can start doing is that, so what I am trying to compute is 28 inverse modulo 75. Okay. So, suppose I am, first of all I should know that whether 28 inverse really exists or not, right. So, therefore, what I will do is that I will find out the GCD of 28 and 75, right. So, therefore, what is the corresponding GCD of 28 and 75. Okay. So, therefore, ideally this should be 1 and I have to check this thing, right. So, 28, if I mean if I divide 75 by 28, I get here 56, and therefore, this is equal to 19, 1, 19, I get here 9, 19, 2, 18, and I get here 1, divide, I get here 0. So, therefore, 1 is my corresponding GCD. Okay. So, the multiplicative inverse really exists. Okay. So, therefore, now you can actually start expressing these things in this fashion. You can write like 75, that is 75 is equal to 2 into 28, 2 into 28 plus 19, right. So, 2 into 28 plus 19, right. So, then what you can do is that you can see 28 is 1 into 19 plus 9, then you have got 19 is equal to 2 into 9 plus 1, and finally you have got 9 equal to 1 into 9. Okay. So, now the interesting thing is that you will see that each of these remainders, that is whatever you are getting as a remainder, can be expressed as a linear combination of the elements 28 and 75. Okay. See, for example, 19 is equal to 75 minus 2 into 28. So, what about 9? 9 is actually 28 minus 1 into 19, okay, but I know how to express 19, right. So, I know that 19 is nothing but 1 into 75 minus 2 into 28. Okay. So, therefore, these I can collect and I can write this as 3 into 28 minus 1 into 75, right. So, what about the next element? The next remainder is 1. So, 1 is 19 minus 2 into 9. So, 19 I know as 3 into 28 minus 1 into 75. This is not point. Okay. So, 1 into, so minus 2 into 9. So, what is 2 and what, so therefore, what is 9? Okay. Oh, I think I wrote the wrong thing, right. So, therefore, 19 is actually 75 minus 2 into 28 minus 2 into 9. So, 9 is 3 into 28 minus 1 into 75. Okay. So, so therefore, this is actually 75. So, therefore, this is actually 3 into 75 minus 3 is 6 minus 2, 8 into 28, right. So, now you see that if you take this final equation and I will write properly. So, this is what? This is 1 equal to 3 into 75 minus 8 into 28, right. So, now suppose I take a modulo 75 on both sides. So, what do I get? I get 1 equal to minus 8 into 28 mod 75, right, because this term goes to 0 in that case, right. So, now what is the multiplicative inverse of 28? It is minus 8, because if I multiply it with minus 8, I get back 1, right. So, therefore, minus 8 mod 75 means 67. So, therefore, the multiplicative inverse of 28 mod 75 is equal to minus 8, and that is equal to 67, right. So, therefore, what was the main objective? The main objective was that at each stage the Euclidean algorithm, whatever remainder we were getting from the Euclidean algorithm, we were expressing that remainder as a linear combination of the starting two elements, that is the mod value, what you are doing modulo with, and the element for which you are interested in computing the multiplicative inverse, right, and that is the main working principle. So, therefore, the main question is that can you express the GCD as a linear combination of 28 and 75. So, after that it is quite easy, because we know that GCD has to be 1. So, if I take a modulo with this corresponding 75, then whatever element I get on the right hand side, the product, the element with which I am multiplying 28 to get back 1 is the multiplicative inverse of 28. Okay. So, this is what I did. So, we can actually, so therefore, the answer is actually minus 8 mod 75 equal to 67. So, therefore, now we will generalize this, but so what is the lesson that we learned? That all the remainders which are generated by the Euclidean algorithm can be expressed as a linear combination of the positive integers a and b. Okay, and although I am not proving, but it is quite easy to prove that the expression is actually unique. So, therefore, you cannot find two such linear combinations which will actually satisfy this. Okay. So, this extended Euclidean algorithm actually generates or computes a linear combination in a very systematic fashion. So, that is the main objective. So, therefore, we will see that the extended algorithm, it just generates or computes this linear combination values in a quite systematic fashion. Okay. So, how do we do this? So, therefore, this is how it is done. So, you define a series of t terms, so t0 to tm, and similarly from s0 to sm, and this is how you define tj and you define sj. So, basically you have a recursive construction. Okay. So, you see that j equal to 0, tj has been initialized to 0, and if j equal to 1, then tj is equal to 1. What about sj? Sj is just the other way around. So, if j equal to 0 and then sj is equal to 1, if j equal to 1, then sj equal to 0. So, this is just the opposite of this definition, 0 1 and 1 0. Why? Because this Tj and Sj is actually used to is the corresponding, I mean what am I interested to do? I am interested to express the remainder as a linear combination of R0 and R1, right. So, now this, I mean the corresponding coefficient in that linear combination is being generated by the series Tj and the series Sj. Okay. So, here the first remainder is, if I start with say R0, okay. So, therefore, if I say that the j equal to 0 R0, so R0 will be equal to 1 into R0 plus 0 into R1, right. So, therefore, the starting point of this should be 1, right. And what about the so in the when this is 1, this is actually 0. So, therefore, you see that when this is 1, this is 0, okay. So, when you are expressing R1, then similarly this Tj has to be 1 and Sj has to be 0, right. So, therefore, Sj is 0 when j equal to 1, then Sj equal to 0 and Tj is equal to 1, okay. But for the rest of the j values, that is when j is greater than 1, that is j is greater than equal to 2, okay. So, in that case, in those scenarios, Tj is defined like this and Sj is also defined like this, okay. So, Tj is what? Tj minus 2 minus Qj minus 1 Tj minus 1. So, Qj minus 1 is the same as that we got in the Euclidean algorithm, and Sj is equal to Sj minus 2 minus Qj minus 1 into Sj minus 1, okay. So, what we can actually prove is that Rj, which is the corresponding remainder value at the jth stage, can be expressed as a linear combination of R0 and R1 with coefficients Sj and Tj, okay. So, the Rj's are as defined in the Euclidean algorithm and the Sj's and Tj's are as defined in the above recurrence, okay. So, why does it work? So, we can see why it works. So, for base cases like for j equal to 0 and j equal to 1, this is trivial, right, that is what we argue. So, let us assume that it is true for j equal to I minus 1 and j equal to I minus 2 and j equal to I minus 1, okay. So, what we will prove is that it is also true for j equal to I minus 1, I mean j equal to I. So, this is basically mathematical induction. So, we are applying mathematical induction to prove this result, okay. So, what type of induction is this? Weak or strong? This is weak induction, okay. So, we apply j equal to I, and so we know we expect the results for j equal to I minus 2 and j equal to I minus 1, and we are proving the result for j equal to I, okay. So, when we are assuming for j equal to I minus 2, therefore, that means that I can assume that R I minus 2 equal to S I minus 2 R0 plus T I minus 2 R1, and also R I minus 1 equal to S I minus 1 R0 plus T I minus 1 into R1. So, these are two given results, okay. So, what about so when I am computing Ri, so that is Ri is the corresponding remainder, then that means that what I have done in that particular step in the Euclidean algorithm is that I have taken Ri minus 2 and I have divided that with Ri minus 1, right, and what was my remainder here? It was Qi minus 1 and I have got Qi minus 1 Ri minus 1 and my remainder was Ri. So, what was Ri? Ri was Ri minus 2 minus Qi minus 1 Ri minus 1, right. So, therefore, Ri is equal to Ri minus 2 minus Qi minus 1 into Ri minus 1, right. So, therefore, I can take this previous two given or assumed results and I can plug in them. So, therefore, I get Ri minus 2 as equal to Si minus 2 R0 plus Ti minus 2 R1 minus Qi minus 1 and Si minus 1 R0 plus Ti minus 1 R1, okay. So, that is equal to, if I take Si R naught out from this, therefore, if I take R naught collect R naught, I get Si minus 2 minus Qi minus 1 Si minus 1 into R0 plus Ti minus 2 minus Qi minus 1 into Ti minus 1 into R1. So, therefore, you see that these two terms are nothing but what is SI and TI. So, therefore, I can write this as SI R naught plus TI R 1, and that proves the case for j equal to I, right. So, that means that the remainder can be expressed as a linear combination of R naught and R 1, where the corresponding coefficients are SI and TI, and SI and TI are defined by this particular recurrence. Okay. So, therefore, I can repeatedly I can keep on continuing these values, these coefficient values, and then I should be able to express the remainder at each stage as a linear combination of R 0 and R 1, right. So, any doubts about this? So, therefore, this is now the pseudo code of the algorithm. So, it is quite simple actually, if you just observe it minutely, it is nothing. I mean, there are there are some temporary variables which have been used, it is just to save some variables, but it is same thing. You see that T 0 minus Q t and S 0 minus Q s are the main things. So, therefore, you are basically computing the T series and the S series. Okay. So, and you are using that to compute the corresponding coefficient values. Okay. So, therefore, finally, what you are giving back by the extended Euclidean algorithm, when you are given two numbers, two positive numbers A and B, you are actually giving back the corresponding GCD of A and B, and you are also expressing the remainder as a linear combination of A and B. So, you are giving back the coefficients S and T, right. So, therefore, how can I use this to compute the multiplicity inverse is quite clear, right. Therefore, I have to just take a modulo on both sides, and therefore, I should get the remainder, right. I mean, I should get the multiplicative inverse if it exists, right. So, this is an example, same example. So, therefore, previously we were trying to compute, we are taking two numbers 75 and 28, you plug in this to the extended Euclidean algorithm, you get the QI series and the, I mean, you get the, these are the corresponding quotients, and this is the S series and this is the T series. So, therefore, you can use this particular recurrence to compute these values. So, you start with 1 0 and 0 1, and subsequently you can take these Q values and you can take these previous T values, because at this stage you know already the previous two stages. So, you can employ this recurrence to compute the values for S 2 and also for T 2, right, because you know the value of S 0 and you know the value of S 1, okay, and you also know the corresponding coefficient, I mean the quotient value. Okay. So, therefore, you can check this, that this works as follows. Finally, what you obtain is this thing, that is you obtain that 1, which is the GCD, is actually equal to 3 into 75 minus 8 into 28. Okay. So, therefore, taking modulo 75, 28 inverse mod 75 is equal to minus 8, right. So, therefore, you remember that this SI was actually getting multiplied with 75, right. So, therefore, if I take mod 75 on both sides, then actually this series I mean, we could have, if we are really interested in computing only the inverse, then computing this SI series is actually of no use, right, because I am actually taking a modulo 75 on both sides, right. So, therefore, actually I can make this algorithm more tailored for the multiplicative inverse computation by actually removing this SI series, because I do not require to compute this, right. Do you, all of you understand this, that it is not required to compute this? Yes. So, this is an improvement. So, note that we do not require the SIs and can take a modulo 75 each time while computing the TIs. So, this will make the algorithm more efficient. So, therefore, I can actually do without computing this column, and the answer which I will still get is minus 8. So, therefore, minus 8 mod 75 means 67, right. So, therefore, this concludes our discussion on the Euclidean algorithm, and then we will take another interesting algorithm, it is called the Chinese remainder theorem. So, basically it is a systematic algorithm which solves a system of congruences. Okay. So, originally people say that it was employed by the Chinese people. Okay. So, therefore, the idea was that suppose they wanted to find out how many people were there in their army. Okay. So, therefore, they used to say that okay, you stand in groups of 5, stand in groups of 3, so in co-prime orders, and whatever is the remainder, which is a small number inside 5 and 3, they used to compute that, and from there they used to find out how many people are there in the army, okay, without counting. Okay. That was the objective. Okay. So, therefore, the idea was that it solves a system of congruences, and suppose m1, m2 and so on as mr are pairwise relatively prime positive integers. So, the system of congruences is as follows: you take x and you report only a1, which is when you take mod of m1. Okay. Similarly, you take mod of m2, you report a2, you take mod of mr, you report ar. Okay. So, this a1, a2 and so on till ar are actually just the the values when you take modulo of x with m1. Okay. So, therefore, this number is definitely smaller than m1. Similarly, this number is smaller than m2. Okay. And similarly, this number is smaller than mr. So, computing these values is actually easy in that case, right, because these are quite small numbers. So, therefore, what you are seeing is that this, when you are solving this x value from this system of equations, okay. So, what you are essentially trying to say is that you are expressing the whole as in parts. Okay. So, therefore, the theme is like to express the whole in parts. So, you see that this algorithm has got lot of applications in cryptography and maybe many other places. So, therefore, for cryptography actually you will see that this algorithm is naturally a secret sharing algorithm. Okay. So, what you are doing is that suppose there is a file, and instead of disclosing the file, and suppose there are R users. Okay. So, I am not giving everyone, I am not giving each one the entire file content. Okay. So, what I am doing is that I am dividing it among say R value, R people. Okay. So, not suppose I divide it among R people in this class, the entire file content becomes evident only if these R people join, right, but not when R minus 1 people join. So, therefore, I can write this information theoretically also. That means that if R people are joining, then the information is total, right, but if R minus 1 people join, then the information is actually 0. Okay. So, you do not have any information of the file. But there is something which is called a threshold scheme. This is not a threshold scheme which I have told you, but this is definitely a secret sharing scheme. Okay. So, Chinese remainder theorem has got so many applications actually. Okay. So, let us try to understand how it works. Okay. So, first let us start with a small example. So, therefore, suppose that x is actually 3 mod 5 and x is 1 mod 3. Okay. So, what is the value of x when you take mod 15? Okay. So, you can verify and the only answer is actually 13 mod 15. So, therefore, the only answer to this is 13. Okay. So, the first thing to explain is why there is only one solution, that is why is there only one unique solution. Okay. So, in order to understand that, let us do one thing. So, let us define one function which is like this. You take x, which is the actual thing which you need to compute, and you express this as tuples like this, like x mod 5 comma x mod 3. Okay. So, you note that what are the possible values of x, since you are considering x from mod 15, there are actually 15 values, right, from 0 to 14. So, for each of them what I am doing is that I am storing 0 mod 5, 0 mod 3. For this case, for example, when the x value is 0, then I am storing 0 mod 5 and 0 mod 3. When the x is 1, I am storing 1 mod 5 and 1 mod 3. Okay. See, for example, when x is 10, I am storing 10 mod 5 which is 0 and 10 mod 3 which is 1. Okay. So, similarly, I can populate this table. Okay. And the thing, or the interesting thing to be noted is that this is actually a bijective mapping, which means that you will never get two 0 comma zeros in this on the right hand side. Okay. So, you see that the domain is actually that there are 15 values, and in the range also there are 15 values, right, and there is actually a 1-to-1 connection. So, therefore, it is definitely a bijective mapping. Okay. So, we will try to prove this, but we will actually give you a constructive proof. So, that means we will give you a solution and also prove that it is unique. Why are? Okay. So, another interesting thing, probably I missed it, or so you see that the m values are actually relatively prime. Okay. So, this will work with any m values which are relatively prime. So, it could have worked with, but therefore, you understand that it has to be it has to be odds, because otherwise they are not relatively prime. If you take two even numbers, then 2 is a common factor, right. So, therefore, this will work if you take two mutually prime numbers. Okay. So, therefore, you can take this as an even number and this as an odd number, but you cannot take two even numbers. Okay. right. So we will try to prove this. Okay. So so therefore you see that we can do like this, that is you take m, so therefore you take 5 and 3 and you multiply these two things. So therefore this is the modular value 5 and this is the modular value 3, you multiply them and obtain m1 by dividing 15 by 5. So when you take 15, you divide by the first modular value which is 5 and you get 3. Okay. And now you see that 3, since you have taken 3 or rather factored out 3, 3 and 5 are mutually co-prime, right. So therefore you can actually compute 3 inverse mod 5 and 3 inverse mod 5 is actually equal to 2. Okay. Similarly m2 also you can compute by dividing 15 by 3 and you get 5, and you can compute 5 inverse mod 3 which is also equal to 2. Okay. So you see that x, which is the actual thing which you are interested to compute, will be equal to 3. So 3 is this value, that is 3 is this value. Okay. And you take 3 and multiply it with 5 and multiply with the inverse value. So therefore you take 3, you multiply with 3 and you multiply it with 2. Okay. Similarly you take 1, you multiply it with 5 and multiply with 2. Okay. And if you take this, this works out to 28 and 28 mod 15 is actually equal to 13. So what is the underlying principle? So we will try to understand that first. Okay. Yeah.
How did you get the second thing in this?
Okay. So let us do one thing. Okay. So let us go ahead and read this, read the solution. Okay. And let us try to understand the principle and then we will go back to this example. Okay. So maybe I could have placed this afterwards. Okay. So let us present a constructive proof, that is in fact this Chinese remainder theorem gives an explicit formula for computing x inverse mod m. Okay. So where m is actually equal to the product of m1 to mr, and what I do is that for each step I compute mi where I divide m by small mi. Okay. So what is the GCD of mi and big Mi? It is of course equal to 1, because you see that all these numbers are mutually co-prime. So if you divide m by mi, so you have factored out mi, so therefore this mi or capital Mi has to be co-prime with small mi, right. So now therefore I can take mi inverse mod small mi, because mi and small mi are mutually co-prime, right. So therefore I can compute yi in this fashion, right. So therefore now you see that yi is equal to mi inverse mod of small mi. Okay. So what I say is that so therefore mi yi will be equal to 1 if I take mod of mi. Okay. But if you take mod of mj where j is not equal to I, then what is this corresponding value? It is actually equal to 0, because mj will divide mi. Do you understand this? That is, if I take mi yi and I take mod of mj where j is not equal to I, then this value will be equal to 0, because mj will divide mi. Okay. So what I say is that this is a, so as I told you, is a constructive proof. Okay. So therefore what I am saying is that this solution will be equal to sigma ai mi yi. Okay. So therefore now you see that what I am multiplying is that I am multiplying with ai and I am multiplying with big Mi and I am multiplying with yi. Okay. So therefore now you see that if you go back to the example, this was the corresponding congruence value. Mi was the corresponding thing when you divided m by small mi. So in that case m was 15 and you had divided that with 5, so you got 3. Okay. And what was the value of yi? It was 2, it was the inverse, right. So similarly you can get the second term also. So the next thing to be understood is that why it is true. Okay. So this you can actually easily check, because so therefore first thing is that we will see that this really satisfies the original system of equation. Okay. So you take this row and you take mod of some mi value. Okay. So if you take mod of mi, then obviously you understand that only for I this value mi yi will go to 1, right. So you will have only ai, but for the other things, that is for the other j values, this will actually go to 0. So only this will result in ai. Okay. So therefore if you take a mod of mi, then the right hand side will be only reduced to ai, right. So therefore what you can do is that you compute this row mod mi So, rho mod mi will be equal to ai. Why? Now, because mi yi is equal to 1 mod mi and mi yi equal to 0 mod mj when j is not equal to y. Okay. So, therefore, the right hand side will only result in ai. So, therefore, similarly you can see that all the system of equations will get satisfied, right. So, therefore, what you observe here is this, that this mapping, or which I call as a psi x or xx, is actually an onto mapping, which means that given any result, that is given any corresponding congruence value, I am always able to find out an x value mod m which will satisfy this. Okay. So, which means that nothing is left out on the right hand side, on the range part. Okay. So, therefore, the next thing to be argued is that this function is actually a bijective function. Therefore, we are actually trying to show is that this is a unique mapping. Okay. So, since the domain and range have got the same cardinality, this becomes quite clear, because we showed that the domain and range has got the same cardinality, and on the right hand side this is also an onto mapping. So, therefore, if you combine these two things, it becomes a bijective mapping. Okay. So, that means that the solution is actually unique modulo m. Okay. So, that means that you not only get a solution, but this solution is actually only one and only one. Okay. This is clear? Example. I gave you an example just now. I gave you just now this example. Na, this. So, what I am interested in to compute is this x equal to 3 mod 5 and x equal to 1 mod 3. Okay. So, I am interested in computing this mod 15. Okay. So, what I do is that I take m. So, therefore, I take 5 and I take 3 and I multiply them, I get 15. Okay. So, then what I do is that I take 15 and I divide with the first mi value. So, that is 3, okay, and then I take 3 inverse mod of 5. So, 3 inverse mod of 5 will be 2. Okay. So, similarly, I take 15 divide by 3, I get 5 and I take the inverse of 5, it is 2. So, therefore, x you can actually write in this fashion. So, this is that sigma thing which you saw. Na? So, this if you open up the sigma, you get this, that 3 into 3 into 2 plus 1 into 5 into 2, it works out to 28 and mod 15 equal to 13. You can check this. So, therefore, this 13 you can see will satisfy the system of equation, because if you take mod 5 it is 3, if you take mod 3 it is 1. Okay. So, therefore, 13 satisfies this simultaneous equations, congruences actually.
So, how the
Cardinality becomes equal from here, na, because you see that your input size is actually equal to what? Yeah, I mean there are 15 values in this case in the domain part. In the range part also you are storing them as these numbers can vary from what? From mod 5 and mod 3. Na? So, the first ordinate will actually vary from 0 to 4. There are 5 values. In the second case also there are 3 values. So, how many possibilities are there? There are also 15 values. So, in the domain and in the range there are, I mean both of them have got the same cardinality. Okay. And at the same time you also showed that it is onto. Okay. So, therefore, it is a bijective mapping. Okay. So, what I am saying is like this, that is, suppose I am giving you some solution here like this, where these are co-prime and all these things. So, they are actually from there you can at least find out one x value for which this is getting satisfied, right. So, that means in the right hand side, I mean you can note that this is like a function. Okay. So, therefore, you see that if I give you some value in the right hand side, okay, in the left hand side you are always getting one value, right. It is not that you are not getting some value. From this function you will definitely get at least one value. Okay. And since the number is same in both the cases, there has to be it is a bijective mapping. Okay. You can also actually formally prove this by pigeonhole principle also, but I am not going to that. Okay. So, but this is quite straightforward actually. I hope you understand this, right. Okay. So, therefore, we will now conclude with some more useful facts, which will be useful for our RSA understanding actually. Okay. So, suppose G is a multiplicative group of order n and G is belonging to G. So, assume that G is a multiplicative group, okay, and has got order n. So, order n means that number of elements are actually n. Okay. So, then the order of G will actually divide n. So, what is small g's order? So, suppose there is a multiplicative group and say there is a G element which belongs to capital G, okay. Then the order of G, okay, I call this as order of G, is actually equal is the smallest number or smallest positive integer, say m, okay, for which G power m is equal to 1, okay. And I am of course, so this is the corresponding unity element, okay. So, the identity element, okay. So, therefore, G to the power of m is equal to I or 1 and mod of m, of course. So, what I am saying essentially is that the order of G will divide actually n. So, therefore, the order of G will actually divide the number of elements in the group G, okay. So, this is actually O means this is the number of elements in G, okay. So, this I am not proving, this is called Lagrange's theorem, okay. So, we will just assume this, okay. Mod m, one mod n, sorry, mod n. So, so therefore, the two natural interesting corollaries are as follows. If you take B which belongs to Zn star, okay. So, Zn star is a multiplicative group that we know, okay. So, therefore, suppose the order of B is say D, okay. So, therefore, B to the power of D should be equal to 1, right, and what is the order of the group Zn star? It is phi n, right, phi n we have seen what is a phi n. So, therefore, B to the power of phi n has to be equal to 1 mod n, because D will divide phi n and therefore, B to the power of phi n is also equal to 1, right. Yes, okay. Similarly, if from this it follows that if n is a prime number, then phi p will actually be equal to p minus 1. So, B to the power of p minus 1 will be equal to b, okay. So, therefore, so therefore, B to the power of p will be equal to b mod p, okay. And this is written in this form, because suppose there can be two cases, okay. One, so here we have written B belongs to Zp, okay. So, first of all assume that B belongs to Zp star. So, what does it mean? Whom does it exclude? Now, whom does it? P is a prime number, okay. So, all elements are co-prime, but if I say B belongs to Zp star, and then that means that from B belongs to Zp, which element am I excluding? 0. I am excluding 0. In Zp actually 0 is there, but in Zp star 0 is not there, right. So, here you see that 0 will satisfy this equation trivially, right. So, therefore, what we need to show is only that when B belongs to Zp star, right, and if B belongs to Zp star, then the previous result holds. So, B to the power of phi p. So, B to the power of phi p means what? B to the power of p minus 1. So, in that case also this holds. So, therefore, this holds for B belongs to Zp, okay. That is why it is written like this, B to the power of p is actually equal to b mod p, okay. But if I had written B to the power of p minus 1 equal to 1, then B would have belonged to Zp star. I could have written B belongs to Zp, okay. Okay, so therefore, so we have seen what is a cyclic group. So, you see that if P is a prime, then Zp star is the group of order p minus 1, and any element in Zp star which has an order which will divide p minus 1, okay. So, in fact, if P is prime, then there exists at least one element in Zp star which has got an order equal to p minus 1. So, what does it mean? That if you take that particular element and if you keep on multiplying, then the smallest number for which it will repeat or it will give you 1 is actually p minus 1, okay. So, there is at least one element whose order is actually equal to p minus 1, and therefore, it is called a cyclic group, because if you take this element, then it will generate all the elements in that field, okay, and finally, it will come back to itself, right. So, therefore, it is called a cyclic group, and this element is sometimes called a primitive element, okay. So, if you remember that cycle that we drawn in context to AES, you take an element, if you keep on multiplying like alpha, alpha square, alpha cube, alpha to the power of 4 and so on, then finally, you get alpha to the power of p minus 1, it will be equal to 1, okay, and p minus 1 is the smallest number for which that happens. So, that means this alpha, if you multiply, it will generate all the elements in that field, right, and therefore the name called cyclic group. Okay. So therefore a primitive element is defined like this: if P is prime, then ZP star is a cyclic group, okay, and any element alpha having order p minus 1 mod p is called a primitive element. Okay. So thus alpha is a primitive element if and only if you take alpha to the power of I, and from 0 to p minus 2 you get actually the entire ZP star. So therefore you can use alpha and compute the corresponding powers, and finally you get the entire ZP star. So therefore alpha generates the entire group. Okay. So alpha is called the primitive element. Okay. So you see that this is an example to clear that. So you take alpha here, okay, and alpha is equal to 2, okay, and you keep on computing the powers. So therefore here your n value is 19, so I am taking mod 19. So that means I am computing alpha square, alpha power 3, alpha power 4, and so on till alpha power 18. So you see the alpha power 18 is equal to 1. So that means now you see that all the elements which are there in Zn star is actually generated here. Okay. So that means what? This alpha is a primitive element because it is generating the entire group. Okay. So you see that there are some elements for which the order is not actually equal to p minus 1, but smaller than p minus 1. But in this case you will find that there are exactly 6 primitive elements. Why? Because this is one primitive element, this is one primitive element, this is one primitive element, this is another primitive element, this is another primitive element, this is another primitive element. So how many primitive elements do you have? There are 6 primitive elements. Okay. So can I justify why there are exactly 6 when n is equal to 19? Okay. So we will try to see all these things. So therefore note that the order of each element, so you can note that the order of each element in Z19 star, and you will find that it will divide the, I mean each order which you take here will actually divide what? 19 or 19 minus 1? 19 minus 1, right. So therefore each order will actually divide 19 minus 1, and primitive element will have the largest order. So the order of primitive element is actually equal to 18, right. So therefore you see that, do you understand why it is a cyclic group? Because you take this, it will go back to 1, means after that if you multiply it will come back to this, right. So it will continue like this. Actually all the elements are cyclic groups. So if you take this, so therefore you take 4, 16, 7, 9, 17, 11, 16, 5, 1, again it comes back to 4, right. So you see that all of them are forming cyclic groups, but only the largest, if you take a primitive element, then it forms the entire multiplicative group. Okay. So actually you can show that any element B in Zp star where P is a prime can be written uniquely in the form of beta equal to alpha to the power of I. So this follows straight from the definition of primitive element, right, where alpha is a primitive element and I lies between 0 and p minus 2. The order of beta, so where beta is equal to alpha to the power of I, is actually equal to p minus 1 divided by GCD of p minus 1 comma I. Okay. And beta is itself primitive if and only if GCD of p minus 1 and I is equal to 1. Okay. So now can you say how many primitive elements will be there?
5.
Yeah. What? You said something.
5
of p minus 1. Okay. So if you take in this case 19, so therefore number of primitive elements will be 5 of 18. So what is 5 of 18? So what is 18? 18 I can write as 3 square into 2. So what is 5 18? 5 of 18 is 6. Okay. I hope you remember that 18 into 1 minus 1 by 3, and similarly you can write that. So this will compute to 6. So therefore that is the reason why you had exactly 6 primitive elements. Okay. So now why is the order of beta equal to p minus 1 also we can justify, I think, little bit like this, that is order of beta is equal to p minus 1 divided by GCD of p minus 1 comma I. Okay. So I will try to give you a simple proof for this, that is if you take say beta equal to alpha to the power of I and let the order of this element be say k, where k is some positive integer. Okay. So that means what? That beta to the power of k should be equal to 1 mod of p right. So, this 1 I could have written as some alpha to the power of some t into k minus 1, t into p minus 1 mod p, where alpha is the corresponding primitive element, right, because alpha to the power of p minus 1 is what, 1, right. So, therefore, this is 1. So, what about the left hand side? It is beta to the power of k. So, therefore, that is alpha to the power of I k is equal to alpha to the power of t p minus 1. So, from here I can actually write that I of k equal to t of p minus 1, right, and therefore, k is equal to p minus 1 divided by I by k, right. So, now certain things becomes important, I mean observable from here, that first of all I of k has to divide p minus 1, because otherwise k is not an integer. Oh, sorry, I by t, yeah. So, I by t. So, I by t has to divide p minus 1, right. So, I by t has to divide p minus 1. And what is the other thing that you observe from here? That I by t has to be a factor of I also, right. So, I by t is also a factor of I, right. So, therefore, now if I also, I mean if I, since the order is actually the least such number, so therefore, it has to be corresponding to the, this denominator has to correspond to the greatest common divisor of p minus 1 and I, okay, because the order is the least such number, right. So, therefore, it actually equal to p minus 1 divided by greatest common divisor of p minus 1 and I, okay. So, this you can prove in any other ways also. So, this is just one sample proof. So, you see that p equal to 13, phi of 13 minus 1 equal to phi of 12, and that is actually equal to 4 or 6. Oh, this is a different example, I think. Okay. So, p equal to 13. Okay. P equal to 13, phi of 13 minus 1 equal to phi of 12. This works out to 4. So, what does it show? It shows that if you take p equal to 13, then there are 4 primitive elements. Okay. So, the question now which I will ask you is that is 2 a primitive element for Z13 star. So, what you will do? The first thing that we can do is that we will generate all the p minus 1 powers of 2 and check that whether it is equal to 1. So, this is quite a lengthy process. Okay. So, actually luckily we have this theorem which gives you a easy check for the primality. Okay. So, for the primitiveness, it says that suppose that p is greater than 2 is prime and alpha belongs to Zp star, then alpha is a primitive element modulo p if and only if alpha to the power of p minus 1 divided by q is actually not equal to 1 mod p for all primes q such that q divides p minus 1. Okay. So, how can I prove this result? So, you see that one part is quite clear, because if alpha is actually a primitive element, then obviously p minus 1 by q being smaller than p minus 1, this can never be equal to 1, because in that case alpha is not a primitive element, right. The other thing that needs to be proved is that if alpha to the power of p minus 1 by q is not equal to 1 for all such primes, then alpha is a primitive element, right. Right. So, therefore, the contrapositive of this would be what? That if alpha is not a primitive element, then there exists a q which divides p minus 1 such that alpha to the power of p minus 1 by q is equal to 1, right. That is a contrapositive. So, we will prove this. So, therefore, we will say that alpha is actually a not, I mean alpha is not a primitive element. Okay. So, alpha is not a primitive element. Okay. So, which means that there exists an alpha power d which is equal to 1 mod p, and what d is actually smaller than p minus 1. Okay. So, we know that d divides p minus 1, right. Therefore, p minus 1 by d is actually an integer value, right. So, therefore, let q be a prime number which divides p minus 1 by d. Okay. So, you see that the moment I am saying that let q be a prime number, so that means that basically what I am saying is that there exists a q for which this is true. Okay. So, therefore, q divides p minus 1 by d. So, therefore, q divides p minus 1 by d. So, therefore, this implies that D also divides P minus 1 by Q. Okay. So, now since alpha to the power of D is equal to 1 mod P, this implies that alpha to the power of P minus 1 by Q is also equal to 1 mod P. Okay. So, therefore, this proves the result. Okay. Do you follow the proof? So, that concludes this particular lesson. So, we have followed from Stinson and also portions from William Sterling's cryptography and network security, and next day we will continue with the RSA crypto system. Okay.